Yeah, so I don't know what happened. My this Apple Pencil, it was not working initially, so I had to stop and connect again. Anyway, so now I think it's fine. So before starting, uh, is my screen visible? 1 second, I'll check. Yeah, I think screen is visible. Yeah, and 1 second. Yeah, audio is on. And what about the pencil? This happened after a long time. I don't know why. Okay, so we'll start. Mm, so basically, in this class, we'll discuss about. In the last class, we discussed mostly about a plain slab or brick kind of heat conduction problem, and that too without any heat generation or something like that. So here we'll discuss more uh, about cylindrical and spherical geometries. First of all, without heat generation, and then with heat generation, and with heat generation both. I mean all slab, cylinder, and spherical. And then some discussion on extended fins or extended surface. Uh, you know, extended surfaces, which are also called as fins, which are useful in some cases. So we'll start. So before going there, first we'll start with the heat conduction through a cylindrical wall or pipe. So in this case, uh, so it will be something like this, and you'll have Ri, which is inner radius. You will have Ro, which is outer radius, and conduction will be happening in this direction, radially outwards. Let's say in this case outward, it can be inward also, but it will be radial. That's the point. And inside there will be Ti temperature, and outside there will be To. So this is surface temperature, and you can have infinity of the ambient temperature far away from the pipe. So this is your pipe. It can be hollow, it can be cylinder also, doesn't matter. But typically this is the case that we have, and from what you say. Mm, so let us assume this is a steady state 1D heat conduction. This is in radial direction, and then no heat generation. So we will have the governing equation as 1 by R del by del R into R into K into T equal to 0. So this is assuming uh, you know uh, variable conductivity and like that. Typically we take conductivity as constant value, so this will come out of the bracket, and then you will have del T by del R. One second. Yeah, so basically you'll have K K by R del by del R T, or it should be square, right? Yeah, it should be square because it's a Laplace, right? So essentially it is this equal to 0. Uh, One second now. Am I doing any mistake? Oh, sorry. It's del by del R only, but there will be one RK dt by dr. So here it will be like that. So here it will be del T by del R. And then, uh, you know, if you integrate it once, yeah, so this is assuming constant K thermal conductivity. So K comes out of the differential. So this will be your 0. It will be a constant because earlier it is 0. And then again, you do one integral, so you'll get C1 ln R plus C2. So now the C1, C2 you can find using boundary conditions, which are at R equal to Ri, you have Ti, and R equal to Ro, you have T0. So this was all done in class, so I'm not going there. The important thing that comes out of here is you get something like Q equal to, that will be basically minus K A dt by dr, and since it's a steady state, you can calculate it at any R and it should be same, otherwise it won't be a steady state. That was also discussed in the class, and it comes out something like Ti minus To. This is your temperature difference across the wall, and ln Ro by Ri divided by 2 pi Kl. L is the length of the pipe. Maybe it should be like shown like this. Yeah, so this will be your L. So this is the important point. This is nothing but the thermal resistance in cylindrical wall. So as we discussed in the slab case, there were two, it was B by K, thickness by K into cross-sectional area. Here it is ln Ro by Ri by 2 pi Kl. And we'll take one problem which is very common problem in this kind of from this topic. So basically, and this is asked at many interview questions also. So it's not a trivial case. So essentially, the problem is you have a cylindrical surface, and you have two options to insulate it. And so basically, I'll just give you the question only. So you have a, let's say, so there are two cases. So you have a pipe, or maybe you can consider it as a hollow rod or solid rod, doesn't matter. Then you have a covering, and you'll have one more thing. So these will all be concentric. Okay, this drawing may be slightly off, but please don't get confused there. So maybe I should draw it bigger. Okay. Uh, okay, so the thing is, it's not looking concentric, right? 1 second, can I do something? Just to make it look more concentric. Yeah, I think this is fine. We can shift this also. So you have a pipe which is in a circle, and it will have R1 radius. Then you have two options. So this is a composite wall, and this is your R3. So basically, this is your pipe or inner rod or something like that, and then you'll have a option of insulating it, but there are two cases. So the yellow represents one insulation material, and then the red represents another insulation material that is available. Yeah, so basically you have two options, and okay, so this yellow material will have thermal conductivity K, and red material will have thermal conductivity 2K. So basically, you have to cover a pipe, and you have two options. First is there are two materials. One is with thermal conductivity K, and there is another thermal conductivity material which has double the thermal conductivity of that of K material, yellow material. So the question typically asks that is asked is so in case 2, you will have outside is K and inside is 2K. So that is the difference. And the question that is typically asked is in which case lower, not lower, lesser heat transfer will take place. So yeah, I mean, same. There will be some Ti and this will be To. So the Ti and To are same. So delta T is same. So only the thermal insulation, which one should we put first and which one should we put second is the question. Okay. So now, as we discussed here, you have to do the same thermal resistance network diagram. And what you will observe is, in case of case 1, we will follow the same uh, classification. So this will be case 1 and this will be case 2. This is very commonly asked question, so I thought I'll take it first. So in case of case 1, our thermal, the total thermal resistance, or we'll put it as, let's say, R1, so that the other will be R2. And so as we seen here, it is ln R2 by R1 divided by 2 pi k, whatever, sorry, 2 pi k into some length L, and then there will be ln R3 by R2 divided by 2 pi, and now the k will be 2k into L. So length is same only. So this will be your total resistance. You can do one thing, you can multiply the first term by 2 and divide by 2, so that you can take 1 by 4 pi k L common, and you will have ln R2 by R1 square plus ln R3 by R2. So the 2 will go to the power of log, because that's the property of ln, natural log. And then you can further simplify 2 pi k L, ln will be there, and then you'll have R2 square, or that R2 and R2 square, 1 R2 will go, so it will be R2 R3 by R1 square. Similarly here, R2 will be ln R2 by R1, but here the 2 pi k, 2k conductivity material is inside, so we will have 2 pi into 2k into L plus ln R3 by R2 divided by 2 pi k L. So it will be thoda different. Again, same manipulation if you do, you will get 1 by 4 pi k L. So the first term will remain as it is, because here you are multiplying the second term by 2. So therefore second term will have square now. This will be R3 by R2 square. And if you further simplify, you will get 4 pi kl. And in this case, you will get ln R3 square divided by R1 R2. So now the question is, which R is better? R1 is better. Which R is higher? Which thermal resistance is higher? R1 or R2? So typically, basically it boils down to this term, right? Because other terms are constant only, and we know logarithmic is monotonically increasing or decreasing function. In which way you see, it depends, but it's a monotonic function, so you can compare the inside terms, so there won't be any problem of sign and all. So the question is, we have to compare R1 and R2. So the simplest way to solve this is let's take R1 equal to 1 meter or 1 mm or whatever you want, R2 equal to 2 mm, and R3 equal to 3 mm. I mean, this is the simplest way, because you can do mathematics. I can give you some idea about it. Basically, you take the ratio of these R1 and R2, and in that case, the 4 pi KL terms will get cancelled. Then there will be ln by ln. Then you take R2 R3 by R1 square divided by R3 square by R1 R2. So there will be some cancellation somewhere. So that way is also there. I'm not denying it. That will be the correct way to do things. And if you do that, let me just give you some idea. So R2 square by R1 R3. So you get R2 square by R1 R3 there, and like that. But you can't conclusively to do that. You need further mathematics manipulation. To avoid that, the simple way, if you get such problems in any exam or interview, you can do this trick. So now, if it is like that, then R1 will be 1 by 4 pi k L ln R2 R3 will be 6 and R1 square is 1, and R2 is same 1 by 4 pi k L, same thing, log of R3 square is 9 divided by R1 R2 2, so 4.5. So therefore R1 is greater than R2. So we know that Q is inversely proportional to R, right? So that's true for all slab, cylinder, spherical, everything, and therefore Q1 will be less than Q2. So so lesser heat transfer will take place. So from here, lesser heat transfer will occur in case 1. So this is very, I mean, leave the mathematics aside. So this is interview question also. Many times it is asked. So here the answer is if you have a lower thermal conductivity material, which is usually called as insulators, and if you have a better conducting material, which is maybe something like steel, not like copper or something. So it is always better to put insulator first and then the other higher conducting material, so that the heat transfer will be lesser or the heat loss will be lesser in this case, because the heat is going from Ti to T0. So that is one thing. So always put lesser thermal conductive material first and then wrap the higher thermal conductive material on the next part. So this is regarding that, and then there is one more critical concept of critical thickness of insulation. So this concept comes in cylindrical also as well as spherical heat conduction problem also. So the idea is same. I mean, the question is thoda slightly different way it is put. So typically you'll have a conducting rod or something like that uh, of some radius Ri at temperature Ti. Typically it is a hot rod or something like that, and then you have to wrap an insulator around it. So 1 second. Okay. And that insulator will have some radius of insulation. So this is your insulation with thermal conductivity K, and then you'll have some heat transfer to ambient, which will be at some mixed ambient temperature H, and there will be some heat transfer coefficient between ambient and the insulation outer surface. So basically, if you uh, write the thermal network for this problem, you will have three type of resistances. So you will have Ti. Okay, I mean, let's take this as uh, T1 and T2 temperatures. So you will have T1, T2, and T infinity. So here you will have 1 by H outer area. Here you will have 1 by H inner area. And here you will have ln R0 by R1 divided by 2 pi. K is the thermal conductivity of insulation into H. Let's call this as H0 just to get the idea that it is outer surface area heat transfer coefficient. and this guy will be HI. So let's say this is inner surface area, heat transfer coefficient. So the question that is proposed is what should be the value of R naught so that maximum heat is dissipated from inside to ambient. So basically Ti is greater than T infinity. So that is the basic assumption. So you want maximum heat loss. So what should be the value of RO? So that is what RO is, the critical radius of insulation or critical outer radius of insulation, and the critical thickness of insulation is nothing but uh, RO minus Ri. So difference. So that will be the thickness, right? So now here similarly, uh, you'll write Q is equal to delta T, which is Ti minus T infinity divided by the total resistance 1 by HIAI plus ln R0 by R1 divided by 2 pi KL plus 1 by HO by AO, and AI will be 2 pi RIL, A0 will be 2 pi R0L. So this is your governing equation for this radial heat conduction problem. Steady state, no heat generation. So now what is happening is it is asked that at what R0 Q tends to Q max. So we need to find at what R0 or R out Q is equal to Q max. So typically what you do is you take the derivative of dq with respect to dRO and equate it to 0, and then you'll get some RO value, which is the solution of that differential equation. And that RO, if you put back into equation number 1, you will get Q max. So and what happens, since we are differentiating with respect to RO, this term 1 by HI will become constant with respect to R0. So only maybe I should write it. It becomes constant with respect to R0. So only these last two terms, will participate in the differentiation. I'm not going into detail differentiation. It's not that difficult also. Basically, you have to, since you are taking differentiation of Q and Ti minus T infinity is constant, basically you are differentiating the denominator. You have to use U by V rule of differentiation, and then you'll get the R0 value for Q max as K by H O. So K is the thermal conductivity of the insulator, and HO is the uh, heat transfer coefficient on the outer surface. And you can put that back into the equation 1, and then you can get Q max. So if you plot it, you get something like this. So this is your Q curve, and this is your RO curve. So you'll realize there is a maxima somewhere which gives you Q max. So this will be the Q max, and this value of R0 corresponding to Q max will be K by H0. So this R0 is called as critical outer radius of insulation, and uh, uh, the difference between RO and Ri is the critical thickness of insulation. Now the important thing to note here is, uh, you know, why did we do all this exercise? So if you focus your attention in this region. When R0 is increasing, your Q is also increasing. So as you put more insulation, more heat is lost. So that is very, you know, unusual. In this case, on this half, we know as R0 is increasing, you are putting more and more insulation, so there will be lesser heat loss from the pipe or whatever the structure is. But in this region, the heat loss increases, and in some applications that becomes important. That's why you should know how much thick insulation you have to put. Typically speaking, for like typically insulation thermal conductivity will be less, let's say 0.1 watt per meter square Kelvin, and in ambient HO will be around 20 watt per meter. I think this is watt per meter Kelvin. Yeah. So if you do that, RO will be K0 by H 0.1 by 20. So that will be 0.1 divided by 20. So that comes out to be 5 mm. So if your insulation is less than 5 mm, the heat loss will be more as you increase the thickness of the insulation. So typically what insulations we put are typically of more thickness. So we don't get, so we get the job of insulation done. But if you put very small insulation, uh, you'll not be getting insulation. You'll be getting the more heat transfer, more heat loss. So in practical application, you should remember this. Okay. Now that is morely, I mean, more or less regarding the what you say, cylindrical heat conduction without heat generation problems. Let me just see if anything is missed, so that we move ahead with the spherical thing. So for spherical problems, you know, yeah, 1 second. Yeah, in case of cylinder, there is one more concept that you should be doing, which is usually asked in some competitive exams. So the question is, there is a cylindrical pipe like this, and which has inner radius of R1 and outer radius of R2. So there is no heat generation. It's a simple steady state heat conduction, radial heat conduction problem, and it is to be replaced by a cylindrical wall, not cylindrical wall, it's like slab, which we studied earlier. So planar slab like brick or something like that. So the the condition is Q should be same. So basically, whatever is Q, the heat was flowing from T1 to, let's say, T2, same heat will flow across this wall also. So from T1 to T2, but they are asking what will be the equivalent area for plain slab. So this slab will have some area, right, through which the heat is getting conducted. So what is that area? Let's say we'll call it as mean area or something like that. So that is the question. Okay. So they are asking about this area, the area which is perpendicular to the flow of the heat direction. And this is, I mean, okay, before I forget, uh, note, okay, we'll talk about this in next section. So before that, we'll finish this. So what happens, as we have seen, again, we have to start from the thermal resistance. And for cylindrical composite wall like this, we know that, and yeah, I mean, this is your material with K thermal conductivity. So in this case also, we know for cylindrical pipe, Q will be T1 minus T2, assuming T1 is greater than T2, will be ln R2 by R1 divided by 2 pi K into L. Okay. So now you can do some modifications. So you can take 2 pi KL in the numerator. Let it be like this, T1 minus T2. And this term is ln R2 by R1. Okay. Now multiply. So do the simple. So this will remain as it is, and T1 minus T2 also as it is. Now, yeah. So we have to do two, or maybe one first. Let's say. Let this term be like R2 by R1. Multiply by R2 minus R1 to numerator as well as denominator. If you do that, so the numerator becomes 2 pi into L. Oh, sorry. K into L. L also you can take inside, no? T1 minus T2. And this bracket will be 2 pi R2L minus 2 pi R1L. And you'll have R2 minus R1 here and ln R2 by R1. So 2 pi R2L is nothing but the outer area. So it becomes K T1 minus T2 A2 minus A1. And this term R2 minus R1 as it is. Now you do one more modification to R2 by R1, which is you multiply it by 2 pi L, both numerator and denominator, and R2 by R1 as it is. So it becomes K T1 minus T2 R2 minus R1 A2 minus A1 ln A2 by A1. Okay. So now we know, we also know for a plane slab, Q is T1 minus T2 divided by B by KA. Let's say M here. K will be same, and let's say B is the thickness of that wall. So let's say BM. So this is BM. So now can write it as K T1 minus T2. Okay, this is becoming congested here, so I'll simplify here. K T1 minus T2 remains as it is, then you'll have some AM by BM term. Okay, so from equation 1 and 2, on comparing equations 1 and 2, we get BM as R2 minus R1 and AM as A2 minus A1 divided by ln A2 divided by A1. So, uh, so this is the, I mean, this is only the answer that we wanted in this question. But you can note down one more thing, that the thickness of the slab is equal to the thickness of the insulation, which is R2 minus R1, which is the same. So basically, thickness of the slab and the thickness of the cylindrical insulation is same. So only the area will change for that slab cross-sectional area. So that will be like A2 minus A1 divided by ln A2 by 1. So yeah, this is, so these are like typical questions that are asked from this topic. I tried to cover some cases so that it's you'll be aware with these terms, so you'll not get stumped if some in some exam you see some question like this and then you don't have any idea. Uh, okay, then we can go to the spherical case. So this one, I mean, this is like the typical problems that are asked from cylindrical, no heat generation, steady state heat conduction thing. We can take some numerical problems also, but I think you can do those. If I have time, I'll take one more later. But we have to cover more things, so let's go ahead. So now next thing is heat conduction through spherical cavity or something like that. So in this case, maybe, I mean, in 2D it will look like cylinder only, but it is a 3D, so keep in mind that. So you will have, 1 second, I will make them. So there is a, now this is a sphere, okay, so keep in mind this R1 is there, R2 is there, some thermal conductivity K will be there. So this is spherical or sphere. In this case, your R thermal becomes I think 4 this R2 minus R1 divided by 4 pi K R1 R2. I mean, so basically your Q is delta T by R thermal. I am hoping you know how this derivation comes. If you don't, I mean, basically this is a 1D heat transfer problem, right? So we know that, let's say you divide this R2 by, I mean, this outer area into small spherical strips. So in that case, your differential heat transfer will be minus K area, which will be function of R, or you should write it. Area will be function of R, and then there will be dt by dr, right? So and we know your R thermal, differential R thermal I mean, along that spherical strip, the resistance, thermal resistance will be uh, dt by dq by definition, right? So if you do that, what you get, dr by minus k ar, and we know the sphere, surface area for any sphere is 4 pi r square. So now we have to just integrate. So r thermal will be integration of this elemental thermal resistance. So it will be integral from R1 to R2 dr by minus k 4 pi r square. So I'm skipping some steps here. So, but if you do this, you'll get R thermal as R2 minus R1 4 pi k R1 R2. You can verify this, but this is the standard formula, and you should get that. So here note which I should not forget, critical thickness of insulation R0 is 2 into K HO. So in like if you compare with cylindrical, only you multiply it by 2. So in case of cylindrical, it is K insulation by HO, outer, not inner. That is also important. And in case of sphere, it just doubles. So the thing is, it comes from, I mean, I don't have time to go into derivation, but when you write the spherical thermal resistance like this equation, what happens in case of cylinder, the area is 2 pi r, but in case of spherical, it is r square, 4 pi r square. So when you differentiate the denominator with respect to r0, here you get k by h0, and there you get 2. That 2 comes from the differentiation of square term of area, which is coming from here. So I hope you got my point. So therefore it is just twice, and good for us that we don't have to remember the formula. That is there. Now one typical formula, one question that is asked from spherical is also, one second, I'll just find it. Like similar to what they did. One second. Root R1, R2, something like that is there. Yeah, so so the question is like that. I mean, when I saw this question, I could not solve it. So I just want, I mean, it's very ambiguous. This is a previous year engineering services exam prelims question, but I have seen this is asked in like different fashions. So basically, this is a, in case of cylinder, you have this question, right? When you want to replace it with a thick slab or cylindrical pipe with the thick slab. So in case of sphere, also they typically modify something like that. And what is the question? The question is, what will be the geometric radius of heat transfer for a hollow sphere of inner and outer radii R1 and R2. This is it. I mean, there is no much more. I mean, there is no other information here. So that's it. So now, how do you solve this question? So basically, uh, as far as sphere is concerned, they have not mentioned any heat generation or anything like that. So we know that Q is nothing but T1 minus T2. Let's say that is the temperatures at R1 and R2 will be R2 minus R1 divided by 4 pi K R1 R2. This is your R thermal resistance. Now you can write it as 4 pi K R1 R2 divided by R2 minus R1 into T1 minus T2. This remains as it is. So for 1 second, you know, we know that for a sphere, uh, surface area, let's say A is nothing but 4 pi R square. Let's say some sphere AM. Now, the only information that we have is this much. So, uh, what they do here is they compare, uh, see here in this equation, this delta T is T1 minus T2, which is not an area term. Thermal conductivity is again a material property. So, these 4 pi R1, R2, and R2 minus R1 are the only terms that are representing the length or the area or whatever length measures. So they compare this with the 4 pi R1 R2 term, and then you get Rm as root R1 R2, and that is your answer. This is what they call as geometric radius. But I mean, one can ask this question that what about this R2 minus R1 rate? So typically what happens if you compare or if you analyze this cylindrical case also, here also you get some, area term which is this much and some length scale which is R2 minus R1. So typically area term will have the unit of meter square and the length scale will have the unit of meter. So you have to go by that logic. This bottom denominator R2 minus R1 represents a length scale and the top 4 pi R1 R2 represents the area scale. So therefore, when you want to compare it to the area term, you need to take only the numerator, not the denominator. And this is your answer. I know this is very, not because the question itself is not that clear. In case of cylinder, the question was pretty clear. So you could say that this is your thickness of slab and this is your cross-sectional area of slab. But in case of sphere, they don't typically give those. I mean, in this question, at least it was not there. But this was one of the competitive exam question, and the options were very confusing also. The options were R2 minus R1, R1 R2, root R1 R2, and R2 by R1. So this was the correct answer. Anyway, moving on, we may take one numerical question from this because we have not taken any. I think there are some numerical questions or maybe other type of question. Let me just check. Because typically the spherical and cylindrical they are studied together, and more or less you solve them in similar fashion only. So let's see if we have any question. Good question we'll take. Otherwise we'll go to the heat generation cases that are also there. Hmm. Okay, one question is there. But before that, let me check if any characteristic question is there or not. generally critical thickness of insulation and this equivalent radius, etc. They are like famous, favorite questions. But let's go with the one question. This one. 1 second. Hmm. So the question is, okay, I think it is internal heating. I think R2 by R1. Hmm. So, okay. Mm, this drawing concentric circles is a challenge. Anyway, so hmm. So it's a composite spherical cavity, and there are two layers. So I'll highlight one with the yellow color, and another with, let's say, mm, orange. So these two are spherical cavities with different materials, and it is mentioned that uh, their thickness is equal inner material has conductivity K and outer will have the twice 2K. So outer is more conducting, inner is lesser conducting, 1:2 ratio. And the ratio of inside diameter to the outside diameter is 0.8. So basically, if you look into this figure, this will be your Ri and this will be your R out. So they have given the diameter ratio, but essentially it is a radius ratio also. And to find, we have to find the ratio of temperature drop across inner layer divided by temperature drop across outer layer. That is the question. So, I mean, I have given you in a very concise form, but the question is, quite lengthy. Anyway, so now here the thing is they have mentioned everything in terms of RO and RI, but you know, uh, we cannot write thermal resistances that way, right? Because let's say if you write thermal resistance here, total thermal resistance, it will be 4 pi K into, let's say this is some intermediate radius Rm, right? So first term will be Ri into Rm divided by Rm minus Ri. This will be your first resistance, right? Oh, it will be ulta of that. So okay, it will be Rm minus Ri divided by 4 pi Rm Ri plus Ro minus Rm divided by 4 pi Ro Rm. But we don't know the Rm, right? I mean, what is the Rm? But what we know is ratio of Ri and Ro. So basically, Ro is 0.8 times, sorry, Ri is 0.8 times of Ro. But very critical information is given in the question that they have equal thickness. So what does that mean? That means uh, for equal thickness of two layers, the necessary condition that comes out is Rm minus Ri is equal to Ro minus Rm. Correct. So this is the thickness, right? So these two thicknesses should be equal. So they are nothing but Rm minus Ri and Ro minus Rm. So by that logic, from there you get, therefore you get Rm as Ro plus Ri by 2. So it is the average of Ro and Ri. Correct. So that is one information you have. But does it give us anything? And and we have Ri by Ro as 0.8, which is given in the question. So your Ri becomes 0.8 times of Ro. Now put that in this equation. So therefore Rm is nothing but 0.9 times of Ro. 1.8 by 2.9. So now you got something to go on. And now I think your uh, this is your total thermal resistance. Now what they are asking? They are asking delta Ti divided by delta To. So temperature drop across first layer divided by temperature drop across second layer. So temperature drop across first layer, let's say if this is your Ti, this is your Tm, this is your T0. So temperature across drop, and let's say heat is flowing from here to here. So delta Ti will be nothing but Ti minus Tm, and Tm minus To will be your delta To. So this is what is asked. Okay. So now we know that since it is a steady state problem, Q flowing through inner insulation will be equal to the outer layer. I mean, uh, the heat flowing through each insulation or each layer of the spherical cavity will be same. Otherwise, it can't be a steady state problem. So therefore, delta T across first layer, temperature drop across first layer will be equal to thermal resistance of first layer, and delta T across second layer will be equal to divided by thermal resistance of second layer. The ratio should be same, right? Then only the Q will be same. Now therefore, from here you get delta Ti by delta To will be nothing but Ri by Ro. Okay, and I think there should be some K here, right? Yeah. Uh, I think here now there will be one K, right? 4 pi K. So here Rm Ri wala, so there will be one K here, and the outer thickness is having 2K thermal conductivity, so 2K will be. So this is your Ri and this is your Ro. So now we put that in the equation here. Therefore, delta Ti by delta To, which is the temperature drop across, ratio of temperature drop across two layers, is nothing but Ri by Ro. So that will be Rm minus Ri divided by 4 pi K Rm Ri into, now we can write it ulta. Since we are taking ratio, we can skip one step and write the other thing as 4 pi 2K RORM, and that will be Rm minus Ro. Oh, sorry, Ro minus Rm. Okay. So now 4 pi K will get cancelled. 2 remains. Rm gets cancelled here. What else is there? Yeah. So this 2. Now Rm. Okay, we'll write it. Rm minus Ri first term remains, and from here 2 Ro remains, and in the bottom Ri is there, and Ro minus Rm is there. See, Rm minus Ri, Ro minus Rm, these are nothing but thickness of two layers, so they also will go away, right? Because they are of equal thickness. So basically what remains is 2Ro by Ri. And we know that Ro by Ri is nothing but 1 by 0.8. So basically it is 2 divided by 0.8. So that is 20 by 8. And if you do the calculation, it should be 2.5. And that is your answer. So what does it tell? It tells you that the temperature drop across first layer, which is the inner layer, which is shown by yellow marks here, it's 2.5 times than that of outer layer. This again confirms our previous observation, right? Whenever you have lower thermal conductivity material, and if you put it inside, the temperature drop will be more in the inside, and therefore the heat transfer will be lesser. So like that. I think this is like one good question from spherical case. Now we'll move on to the heat generation. Heat generation. Let's say we'll take in plane slab. So first case we can take of plane slab. So in case of, this is again steady, not it is a 1D problem, and one second, I'll take some water. So we knew in case of plane slab, I mean we studied this in previous class also, something like that. So there are many cases here, but typically two of them are asked or expected from you. So let's say this is your domain and this is your x direction. So this is your x equal to 0 and this is your x equal to L, and heat is flowing something like this. It can be anything, but let's say this is your heat conduction direction. So that means T1 will be greater than T2. Let's say this is your problem statement, and this is 1D problem. 2D problem we'll discuss, I think, in subsequent classes in this course, but let's say this is a 1D problem. Okay, now we knew that you know for simple slab without any heat generation, this was the governing equation. But now there is a heat source, volumetric heat source. What do you mean by volumetric? It means that heat source will be having constant value throughout the volume of this slab. So if you consider that, let's say we denote it by Q dot. So there will be thermal conductivity, and this will be a governing equation now. And typically the way it is solved is, this is nothing but a constant, because you assume the volumetric heat source to be a constant, and therefore again this is like a second order ODE. So when you integrate it once, you get dt by dx as minus q dot by k into x plus c1. If you integrate it again, you'll get minus q dot by x square by 2k plus c1x plus c2. Now there are two unknowns, c1 and c2, and you can find them using two boundary conditions, that at x equal to 0, t is equal to t1, and at x equal to l, t is equal to t2. I mean, I leave that up to you, but this is the way you get the temperature profile. Now, uh, I mean, there are two things to know here. Since there is heat generation, uh, since the heat generation term is not zero, temperature inside the slab can be greater than T1 and T2. So earlier we knew that from T1 to T2 heat conduction is happening, and if there is no heat generation, one surface will be at the maximum temperature and another will be at the minimum temperature, and there will be linear decrease or increase depending on the nature of the thermal conductivity. But in this case, it can be anything. And usually inside it will be hot because there is a heat source. That is one thing. But in case mm, but in case if one wall is insulated, in that case, mm, if one of the wall is insulated, temperature will be maximum at that wall, since dt by dx has to be 0 there, because when it is insulated, the temperature gradient with respect to x direction should be 0, and therefore it should be horizontal line as far as this figure is concerned. And let me just confirm once if any other thing is to be said here. As far as I remember, that is the case, because at x equal to, let's see, if we take this problem only and assume that at x equal to 0 we insulated. So if you do that, dt by dx is 0 at x equal to 0. That means C1 is 0. That means at x equal to L, T2, so C2 will be T2 minus this term. So that will be T2 minus T1 minus L square minus x square. L square minus x square will be the radiation. and it goes from 0 to L. Yeah, I think I'm correct here. Okay, so now we'll take some problems. I mean, there are like lot of variations here. I mean, due to constraint of time, we cannot take more, but I assume you get my hint here that it depends on how you phrase the problem, but there can be different things here. And one more thing, if let's say there is heat transfer to the ambient and there is some H and T infinity, since it's a steady state, not steady state, but whatever heat is generated in the slab, that will go to the ambient. So by that logic, I mean, if you write the energy balance, one second. Hmm. So you understand that, right? Whatever uh, one more thing here. One more thing I had to say, which it skipped my mind. I was going to say that. One second. Ah, so this is your first note. Second note, you cannot draw or use resistance network uh, analogy inside the slab. The reason is here between T1 and T2, the temperature is function of X. How it varies inside the slab is function of X. So you cannot use, just that formula R2 by R1 or B by K. Those won't work here. But you can use them outside. So from the wall at X equal to L to the ambient at T infinity, you can still draw that 1 by H A kind of analogy. And by energy balance, heat generated in slab will be equal to heat convected to surrounding. I mean, this is strictly in steady state. And we are dealing with steady state only, because otherwise in this governing equation there will be an unsteady term. And in some problems we should also remember that this will also be equal to the heat conducted to surface of slab. So what I mean by this is, that is heat conducted in the heat generated in the slab will be Q dot into, since it's a volumetric heat source, you have to multiply by volume of slab. So this will give you the energy per unit time. And heat convected to the surrounding will be H A2 T2 minus T infinity. A2 is the wall area at X equal to L. And heat conducted to the surface will be minus K into A2 dt by dx at X equal to L. In some problems, they ask this also. they will ask that what is the temperature gradient at outer wall or at x equal to or something like that. So you should remember this also. This is also important observation. In some problems, you have to use this also. Anyway, so that is it. We'll and see if I mean I need not explicitly tell this, but if T1 is equal to T2, you will have symmetric temperature profile, and therefore at x equal to L by 2, you will have dt by dx equal to 0. But if T1 is not equal to T2, then it is different case altogether. You cannot say anything like that. Okay, so we'll take some problems. One second. I think this type of problems are there in your assignment also. But anyway, we'll take some problems and see. This is a good problem. So it's a previous year GATE question, 2007. And it is a combined question. So there are two things that you need to find out. So there is a plane plate like this. And one face is maintained at 160 degrees. One is at 120 degrees. This is your, let's say, 0 point. So this is your 20 mm. The thickness of the slab is 20 mm. And we know since the high temperature is here, so this will be your heat conduction direction from high to low. And there is an uniform heat generation source which is at 80 megawatt per meter cube. This is your heat source, volumetric heat source. And thermal conductivity of the plate is 200 watt per meter Kelvin. They have not mentioned what type of plate it is. They are just given constant thermal conductivity of 200 watt. And you need to find first location within plate where T is equal to T max. So basically, where is the maximum temperature point and what is T max? So how much temperature is generated in the maximum temperature that is generated in the slab. So again, you can refer to these equations. So we can take help of we can take this equation we can use, right, because that's the temperature variation that we can directly use. So we have T is minus q dot x square by 2k plus c1x plus c2, correct? Now we know at x equal to 0, T is equal to 160 degrees, and at x equal to L, T is equal to 120 degrees, and q dot is 80 megawatt per meter cube. So you can convert it into SI units. 8 into 10 to the power 6 watt per meter cube. Okay, so and K is 200. So everything is given. So this will give you a temperature profile. But see, in first question, what is asked is at what location the temperature is max. So that's the better way to do is and also we have this dt by dx, right? So dt by dx will be which is nothing but this. This is q dot x by k plus c1. Correct, no? Uh, yeah, but we don't know c1. So anyway, uh, we have to solve this equation. So we'll come back to this later. So now let's put x equal to 0. So therefore, from first boundary condition at x equal to 0, t is 160. You get C2 as 160 degrees Celsius. Now put second boundary condition. You get 120 as minus 80 into 10 to the power 6. L is nothing but 20. So that is 0.02 meters square divided by 2 into 200 plus C1 into x is 0.02 plus C2. This is nothing but 160 degrees Celsius. So in this equation there is one unknown, that is C1. So if you solve it, you should get C1 as 2000. Okay, and it will be, the unit will be degree Celsius per minute because it is multiplied by x. Meter, sorry, not minute. Therefore, uh, and also now you can use, and also we have dt by dx as minus q dot x by k plus c1, and it will be 0, right, at Tmax. That is the definition of Tmax. That slope will be 0 there. So now we can put the things and you can get x, let's say x prime, where t is equal to Tmax. Therefore minus, or you can uh, you know, x prime will nothing but c1 into k by q dot. Just a manipulation. And c1 is 2000, k is 200, q dot is 18 to 10 to the power 6. So this is 5, 6. So basically 400, 4 by 800. So 2 by 400, 1 by 200. So that will be 0.05 or 0.005 meters. So that is 5 mm. So basically from uh, x equal to 0 at 5 mm you will have maximum temperature, and Tmax will be, now we have to put x equal to 5 or 0.005 meter in the temperature equation, which is equation 1, and you get Tmax. Now uh, I am leaving the calculations to you because we have limited time here, but you should get 165 degrees. So see, answer you can get, but the main point that I am trying to make here is now if you plot the variation, it will look something like this. Let's say this is your x equal to 5. So it will be like this. And this will be your 165 degrees Celsius. And this will be your 5 mm. So this is the point that I am trying to make, that whenever there is a heat generation in a slab or anywhere, the inside temperature will be more than T1 and T2 unless and until one of them is insulated, one of the walls. Okay, so this is it. Now we can go for a cylindrical wall heat generation. So See, actually we have limited time, but again, in cylindrical wall, you have to do the same thing. Uh, just that the governing equation changes here. In case of cylindrical wall, so this Laplace, or not governing equation, this Laplace will change. In Cartesian coordinates, this is like this. In cylindrical coordinate, it will be 1 by r del by del r into, I think k comes out, right? So let me just confirm. Uh, if you take k out, basically, uh, yeah, and you have to take, I mean, you can multiply r on the both sides also. So you get del by del r del t by del r plus this heat generation term, and this r by k factor multiplies here. So this is your governing equation becomes, and your r belongs in this range 0 to r or whatever is your uh, oh sorry, I mean this changes. This is, I mean, sorry, it can be anything, depends on the problem. And now how do you solve this? I think we have done this in class also. But basically what you essentially do is the same thing as we did in the uh, what is it, cylindrical, sorry, 1 second. Mm, I'm just seeing if any question is there so that we can directly go to the question rather than solving it and again doing that way. Hmm. Typically, I mean, in competitive exams, they don't ask these questions unless and until it is gate, because you need a lot of calculation and all. Anyway, we'll see if any question is there so that we can take it. Otherwise, we'll see. Hmm. So basically, I'm not able to find a good question. Uh, so the way to do this is, again, you take this term in, you know, del t by del r minus q dot r by k, and then you integrate it once, so you get r del t by del r, which will be minus q dot r square by 2 k plus c1. Now you divide it by r on both sides, so you get minus q dot r by 2k plus c1 by r. Now you again integrate it once, you get minus q dot r square by 4k plus c1 ln r plus c2. Now it depends, uh, you know, on the boundary conditions. This c1 and c2 again you have to find from the boundary conditions. But only thing that you should be careful about, uh, you know, sometimes what happens, there is no R1. They will mention that it's a thin cylindrical heater wire. So they will give you the thickness of the wire or the radius of the wire and current flowing through it. So you can get the heat source as I square R. Those information will be given to you. R is the resistance of the wire itself. And but in that case, what happens? There is no uh, R1. So R1 is 0. So in this equation, you cannot put R equal to 0 because then this logarithmic of 0 is not defined. So in that case, you have to make uh, this term C1 ln term as 0 by putting C1 as 0. Uh, Note that C1 is not always 0. In some problems, it can be non-zero, but in some problems where the R1 is 0 or the inner radius of that cylindrical wall is 0, for example, in case of a thin cylindrical heater wire, in that case, you have to make this C1 0. Otherwise, you have to solve like what we did earlier. And here also what happens, uh, whatever from energy balance, uh, Q dot, which is the heat generated, into pi r square L, that is the volume of the slab. So this is the total heat generated per unit time, and it will be conducted to the environment. So it will be area is to pi r L, and that wall temperature and minus the ambient temperature. So in some problems you need this also. So if you simplify this, you get Q dot R by 2H plus T infinity is equal to wall temperature. So again, I mean, and this is same in case of spherical also. So in case of sphere, what happens? In case of sphere, here again, the governing equation is like this. Del by del R, R square del T by del R plus Q dot R square by K equal to 0. This is a steady state again, but spherical coordinates. So then again you integrate it once, and then you get del square R square del T by del R minus Q dot R cube by 3K, and this del T by del R becomes minus Q dot by R by 3K plus some C1 constant, and then this will become C1 by R square. And then you again integrate it once, so you get minus Q dot R square by 6K plus this is 1 by R2, so minus 2, right? So you'll get, in case of sphere, you get minus C1 by R as the integral. And then you'll have C2. Now again, here also note, uh, I should write it for some people who don't attend. Here also note, as R tends to 0, uh, C1 tends to 0. Basically like that, you have to remember. Here also, as R tends to 0, make C1 0, so that your solution will be finite. Otherwise, you cannot solve this problem. Because in sphere also, as I said, there is no guarantee that you know that R is 0 at because as we did earlier, there can be composite cylinder problems where R1 can be non-zero. So in that case, you have to solve it by making it non-zero. But if it is a spherical heat source without any R1, in that case at R equal to 0, you have to make the slope, the temperature slope condition dt by dr del T by del R as 0. Therefore, you have to make C1 0. There is no other option. And similarly, the energy balance gives Q dot total heat generated into volume. Volume of the sphere is 4 by 3 pi r cube, or let's say r is the radius of the sphere, or maybe I should not write r, maybe let's say r2, whatever is the outer radius. is in h into 4 pi r square r2 square into t wall minus t infinity. So t wall is nothing but the outer spherical cavity radius. So from here also you get q r or uh, r2 divided by 3h plus t infinity equal to t wall. So like that. Since we don't have time, we are not taking problems, but you get the point, right? These are basically second order ODEs, and you have to solve them like that. The constants are determined based on the boundary conditions, and in some cases, you need to take the help of energy balance in order to determine the wall temperature. Okay, then we have 15 minutes now, so we can just quickly touch upon the topic of fins, which was, uh, if you have attended the classes, uh, the derivation for the extended surface variable cross-sectional area. It's very interesting derivation that you should all go through. It may not be asked in the exams, but it's good to know that there exists such thing, because in some competitive exam interviews, for example, especially ISRO, BARC, it's, R&D kind of, not PSUs. In PSUs they won't ask you that detailed, but in case of BARC, R&D, BARC, ISRO, DRDO, they may give you a fin with variable cross-sectional area, and in that case, you cannot use the general formulas that you use. You have to go from the first principle which were discussed in the class. But nonetheless, since that is already discussed and we have limited time, we'll go through the important things regarding the fins. And you know, uh, one thing is there that first of all, uh, we'll discuss only constant cross-sectional area fins. Uh, in this case, uh, you know, if the fin is like this, something like this, it's a typical rectangular fin. There can be a you know circular fins as well, something like this. So, in all of these cases, you should understand that, let's say if this is the thickness and this is the z dimension and this is the length of the fin. In this case also, this is a pin fin they call it sometimes, and let's say if this is the diameter of the pin of the fin. So here periphery will be 2z plus t, cross sectional area will be zt. Here periphery will be pi d, cross sectional area will be pi 4 d square. This should be clear to you. And general governing equation is nothing but c1 e to the power mx plus c2 e to the power minus mx equal to 0. Here x is a length coordinate from 0 to L, and m is nothing but a number like constant like hp by k. Keep in mind that M will have units of 1 by meter. I should not write 1 by M because M itself is the symbol. So, or maybe I can write it this way because this question is also asked somewhere sometime. The dimensions of M are nothing but L power minus 1 or L power minus 1. Is it so? 1 second. H is watt per meter square Kelvin. Perimeter is meter. Watt per meter Kelvin meter square. So what goes? Kk goes. M remains. 1 second. M is HP by K. Correct. Watt per meter. 1 second. Is it 1 by meter square? One second. I just want to confirm it. I don't want to give you wrong data. Yeah, I think it is 1 by meter square. In that case, this becomes e to the power mx. No, it should be 1 by meter only because typically it is 1 by ml, right? So, I mean, efficiency is 1 by ml. So, yeah, it should be 1 by meter only. And I don't know. I'm getting confused. But it should be length power minus 1 only. Otherwise, it won't dimensionally be correct, no? It is root, no? Correct only. This is correct. There's a square root sign, so meter square, 1 by meter square will become 1 by meter and in the root. Anyway, so you have the big formulas from the class, but I'll focus my attention on three cases. Case one is infinite long fin. So in that case, your theta by theta 0 becomes e to the power minus mx, and heat transfer from the fin becomes under root hpka into theta 0. What is theta 0? Theta 0 is base temperature minus infinity temperature. So your base will be at certain constant temperature and your ambient will be at certain temperature. Same for this case also. So this is constant. Theta 0 is constant. And what is theta? Theta is your temperature variation, which is T minus T. Basically, they non-dimensionalize the temperature and they write it this way. Second case is fin with adiabatic tip. So in this case, dt by dx at x equal to L is 0. And then you have theta by theta 0 as cos hyperbolic m L minus x divided by cos hyperbolic ml. And the heat transfer through the fin will be under root HPKA into theta 0 into tan H ml. Okay. Now, like, there are two more cases. One is fin with finite length and uninsulated tip. So there is a significant heat loss from the tip also. So in that case, mm, actually the formula is very big. I can give it to you, no problem. Okay. Uh, I mean, it was given in the class also, but okay, I have to give you 1 point, so I'll just write it down here. Cos h m L minus x plus h by mk sin h m L minus x divided by cos h ml plus h by mk sin h ml. And Q heat transfer through the fin is theta b HPKA into sin HML plus H by MK cos HML divided by cos HML plus H by MK sin HML. So typically what they do in this case, they make some approximations. Assume corrected length LC as L plus T by 2. So L plus thickness of fin by 2, or in case of fin L plus D by 4. And what they do, they neglect these terms which are multiplied by H by mk. Uh, I mean, it's a hack basically to not memorize these big formulas. It is observed that you get similar solutions, not exact but approximate. In that case, it becomes cos h m LC minus x divided by cos h ml LC, and Q fin becomes theta b HPKAC or HPKA into tan HML. See, uh, again, I mean, this is like approximate solution because you introduce some corrected length and you neglect this, uh, neglect these last terms here. Anyway, and then there is fourth case also, but I don't have that formula with me. Uh, but this should suffice, right? Okay, so the fourth case is fin with finite length and tip at constant temperature, let's say TL. But this is very rare actually. There is a big formula for this also. You can find it in some book, but usually it is not asked in any competitive exam, because in practice also you don't get to see any tip which is, at certain, its end is at certain temperature. It may happen if the fin is between two source and sink. That can also happen, but I think that is a problem for conventional questions. And right now we don't have time also. Actually, I don't have that expression also with me. Otherwise, I could have given it to you. I have temperature one. I think it was given in the class, but I don't have the heat transfer Q fin. Anyway, the main point that I wanted to convey here is because these expressions you already know. They were discussed in class also, and you may have them from somewhere else also. But other than that, there is this important thing called as fin efficiency. Typically, we write it eta, and it signifies, you might be knowing that uh, whatever heat transfer is taking from Q fin, and uh, heat transfer from the fin if all fin surface area is at TB, base temperature, which doesn't happen usually, but this is like the hypothetical case. And uh, what will this quantity will be? It will be H into P into L into TB minus T infinity, because PL represents the whole curved surface, surface area, and that's how you do it. And there is something called as fin effectiveness. Typically, it is written like this, and it is Q fin divided by Q through base area of fin. So if there was no fin, there will be some area which was, and this should be greater than 1. Then only it makes sense to install the fins. Otherwise, why are you installing fins? And this is nothing but HA into TB minus T infinity. So from here you can get some, uh, you know, this thing, what you say. If you, from efficiency and effectiveness, if you get Q fin, it basically boils down to efficiency into P into L equal to effectiveness into base area. Sometimes this also is an important correlation in some questions that you should know. And also one important formula that you should remember is the effectiveness is proportional to K M by H. And K M is again, I mean, I will tell you. Yeah, so if you further simplify, if you don't want to remember it in terms of M, you can just replace it by M formula, which is HP by K, and then if you solve it, you get uh, Kp by Ha. But this is actually confusing to remember this. So what I do, I only remember M formula because it is used everywhere, which is HP by K, and you remember that effectiveness is proportional to Km by H. So that's how you can remember. And from here you can draw important conclusions that effectiveness is higher for low heat transfer coefficient. So therefore, they say that uh, uh, you know you always put fins where heat transfer coefficient is low. In one of the exam, the question is asked that in interview, the question was asked, what if I put the fins on the side where the heat transfer coefficient is higher? It doesn't matter. That's just a waste of material, because anyway the heat transfer rate, overall heat transfer rate, will be decided by the side which has lower heat transfer coefficient, and therefore it makes sense to put fins there. If you put fins where H is more, then it's just a waste of material. It won't do any good. And again, the second conclusion is effectiveness increases for high K values. So therefore, fin material should be a highly conductive, thermally conductive material such as aluminum or copper. One more thing is effectiveness increases for higher perimeter by area ratio. That means your cross-sectional area will be less and the periphery should be more. So that means thin fins with higher number density. So they should be as close as possible and they should be thin as thin as possible. The lower limit for fin spacing is decided by boundary layer. Boundary layer thickness between two fins. So basically, it like you can keep them as close as possible, but not very close. If their boundary layers interact, then there will be reduction in heat transfer because of the nature of the boundary layer. And again, all these formulas that we discussed, they are for a single fin. So it may happen that at some in some problem they will give you that there are n number of fins, and then you have to solve. So in that case, you have to multiply n with the q fin formulas. And in case of ineffectiveness also, there is no need actually. But you just have to, in case of inefficiency, you have to be careful. Uh, Wherever the area is there you have to be careful that what type of area, because the total heat transfer will be heat transfer through the fins as well as heat transfer through the area where there are no fins. So that will be a total heat transfer. So you have to keep it that way. Okay, then I think we are over time, so I'll stop here today. We could not take any problems in fins because of the time limitation, but I tried to give you as much as um important thing as possible. And one more thing, mm, for that infinitely long fin, tan HML, there is a limit. I think 5. 1 second, let me check. See, tan hyperbolic value becomes uh, very high, I think, after 5 or something like that. But yeah, I mean, when do you consider fin to be, infinitely long? So, okay, I got it. Uh, so, if tan HML value is greater than 5, fin is considered as infinitely long. This is also one hack, or one I saw it at one place. Anyway, so we'll stop now, and I'll see you in the next class. Okay, bye.